and welcome to episode number 11 of CS350 Online. I'm your host, as always, Leslie Eisted, and in today's episode, we are going to take a break from going through the course modules, and we're going to spend some time focusing on assignment 2, because, of course, assignment 1 has now been submitted, and I hope that you've had a chance to do that. So assignment 2 comes next. Now, a couple things that I want to say about working on assignment 2. The first one is that the guide for assignment 2 is actually split across 2 different files. So there's A2A and A2B. And the reason for this is up until last term, they were 2 separate assignments. And many years before that, they were 1 assignment, and we've actually decided to put them back together into a single assignment because we want to start making changes to CS350, updating some of the assignment content and stuff. So it's back to a single assignment, and the guides you need are A2A and A2B. The one thing I want to say, and I cannot stress enough, is that it's really critical that you start this assignment early. You have everything that you need for it because we've covered all of the process section. The reason why it's important to start early is it's not that the code is going to be difficult. The problem is that the synchronization and deadlock issues are particularly difficult to debug. So I've seen people take like a day or two to actually write the code, but then at the end of the day, they spend the next 2 or 3 weeks just debugging simple problems. Now, I'm going to make a post on Piazza to let you know where most of the problems actually come from and how to kind of debug the weird memory errors that you get. Please make sure before you ask a question that you check the Piazza post to see if it's one of the common errors, because that will help debug your stuff. But we'll talk more about that in a minute. First, of course, OS of the day, right? So this operating system is one that I'm betting most of you haven't heard of. It's not a commonly known one. It's called Alto Executive, and this was released in 1973, and it's a product of a place called Xerox PARC, and it was produced for the Xerox Alto. Now, this is a really interesting one for a lot of different reasons. So number one, for those of you who've never heard, I presume you've heard of Xerox, the copy company, but you may not have heard of Xerox PARC. Xerox PARC is a very famous computing research facility, and they have brought to you so many things that you use today that we wouldn't really be here today without the research that they've done. So things like object-oriented programming, LAN, the list is actually really big, and we'd spend a long time going over all the list if we would actually read it out. So Xerox PARC is a pretty famous research facility. By the way, they do take interns. And you're welcome to go onto their website and take a look if anything interests you. PARC, by the way, stands for Palo Alto Research Center. So if we ever get back to in-person co-ops, when you want to go to California, Palo Alto is California. Right beside Mountain View. Quick question on Twitch. We are going back to 1 assignment. What does that mean? So assignment 2 actually used to be 2 assignments. Okay, so it started out as a single assignment, probably 10 years ago. And then about 5 or 6 years ago, we split it into 2 parts. And then we've decided to recombine it back into a single assignment for various reasons. One of them being that when assignment 2 was 2 parts, if you got caught cheating on A2A, it really screwed you over for A2B because they're so interdependent on each other that if you messed up A2A, and you had to redo it in the couple days before A2B was due, it was just an absolute nightmare. So we're trying to bring back a bit of fairness into this. We'll see how it goes. All right. Anyways, back to Alto Executive. So there's a couple interesting things about this operating system aside from where it came from. One of them is the computer that it ran on. And there's actually a picture of it down here. And you might be thinking, wow, this is not a room-sized computer, because it's not a room-sized computer. It's about the small size of a small fridge or filing cabinet. And it's on wheels because it's obviously quite heavy, to be honest. be nice if all computers were on wheels, maybe except laptops. So in a lot of ways, the Xerox Alto was actually, I want to say, the first personal computer, like a computer that was meant for one person and was one person sized. And this little computer here had a regular keyboard. I mean, it probably weighed 20 pounds, but it had a 3-button mouse, a 5-chord keyboard, which you can't see in the picture. It also had Ethernet connectivity. So it had all kinds of things that you would expect. And before you sit there and you're like, wait a minute, that monitor is in the wrong orientation. They have it on the side. Actually, they don't. That is the correct orientation of the Alto's monitor, is portrait. And the reason for that is because this computer was really designed to be working on office documents, and most office documents are not landscape orientation, they're portrait orientation. So it's meant to mimic what a sheet of paper actually looks like. Now, the operating system itself had a lot of the features and functionality that you would expect at the time, so things like time sharing, concurrency, and so on. But it also had Ethernet support and support for LAN, so they actually had games at Xerox going over LAN with the system. But there is one interesting thing they did. So number one, this operating system had a mouse-operated desktop environment. And it's like the first of its kind to actually have a mouse-operated GUI. And in order to make that work, they had to break the isolation between kernel and user programs. So user applications needed to actually be able to access the underlying microcodes in order to optimize themselves to give a really good response rate for the programs. So we're not as isolated as we would traditionally be, but I don't think they really saw security as being a big deal with these. And in 1973, I certainly wouldn't have either. And my understanding is there was only a few thousand of these machines ever made, and they were ridiculously expensive to get your hands on. My understanding is at the time, Steve Jobs actually had stopped by Xerox to learn about Alto Executive and the Xerox Alto, and he didn't buy one. And I think it was because it was just too much money. Like, I think they were like $20,000, and that's a pretty big personal investment at the time, way back then. Now, at the bottom here, I actually have some of the icons that were used in the desktop environment. And these are icons you probably recognize. So there's an empty folder, an empty document, a database file, a printer, and a trash can. And these are all icons we still use today. They come from 1973. They don't come from Windows. They come from Alto Executive. Now, what kinds of applications did they have? They had office applications, code applications. So I'm pretty sure Smalltalk is actually from Xerox PARC. They had email applications, drawing, and some different games. Now, here is actually some screenshots of Alto Executive, which is kind of cool. And you can see here, we've got overlapping windows. We've got a little mail icon and a clock and a calendar. Yes, it is dithered black and white. That's all the screen supported back then. But hey, this is huge progress, right? But you can see here that you can actually browse through code. Yeah, this is definitely Smalltalk looking at it. You can browse through the code, and it had like IDEs, very modern ideas, right? That's really, really cool in my book. And then this other one is a common test image they used from one of their paint programs, these pigs under this dithered rainbow, which is kind of cool. All right, so that is Alto Executive, and my understanding is this operating system has actually inspired a lot of the desktop environments that you see today, and in particular, the Mac operating system desktop is actually heavily inspired by this one. So, it's a very influential OS. All right. So, let's get into assignment 2 discussion. And for those of you who have been watching live, my apologies. I think my internet has gone down or is being very, very, very slow. So my sincere apologies. Have no worries if the live feed ever goes down. We are actually recording to my disk as well. And I upload all of the recordings to YouTube afterward. Just appears to be a bit unstable. So we'll see what happens. So I'm going to dive into assignment 2 now, and hopefully this will actually come back. Okay. All right. So again, I apologize for the frame drops. The full, complete, non-frame droppy version will be posted to YouTube afterwards. So don't worry too much. My internet connection seems to be all over the place right now, and I'm not entirely certain what's going on there. So assignment 2 actually has 3 parts to it. And the first part of the assignment is actually very, very easy. It's very straightforward. So I'm going to go on Piazza and talk about the first part of assignment 2. And that is, we want you to implement locks and condition variables. And you absolutely have to do this first. If you don't do locks and condition variables first, you can't even attempt the other parts of the assignment. It's just not going to work. So the lock implementation, as we actually went over in class, the pseudocode for the lock acquire function can actually be found in Piazza in that extra sample problems thread. After you have implemented locks, you need to test locks. And the tests that we use for locks is SY2 and I think UW1, or UW test. So there are 2 lock tests. Now, testing locks is tricky because you can run the test once and succeed, but maybe if you ran it 10 times, one of the 10 times would fail. There's no surefire way I can tell you to test your locks that gives you a guaranteed yes or no answer your locks work. What you need to do instead is be statistically certain that your locks are working. So my recommendation is to generally make a script and then have the script run the test, 100 times or 1,000 times. And then after you have validated that that is actually working, then what you want to do is actually change the number of CPU cores. So let me show you how to do that in OS 161. Oh, looks like my terminal window is on the other screen. There we go. Yeah, I've been writing code in Python. Fun stuff, right? Not really. Okay, so in your root directory, you will see a file called sys161.conf. And if you go to the very, very, very bottom of the file, you can actually tell OS 161 how many CPUs you want it to use. And my recommendation to you is after you have validated your locks 100 or 200 times on a single CPU, if you want to increase the chances of a race condition, increase the number of CPUs. And then rerun the test. Now, it's going to be very, very, very tempting for you to run it on 4 CPUs as your test to start with. And I don't recommend that because if you do find that they failed, it's much harder to debug it on several CPUs than it is to debug on a single CPU. And for the question on Twitch, if it succeeds 999 out of 1,000 times, is it considered working? No. No, it's not. Because it means there's a race condition and there's something wrong with your lock. And the problem is, just because it took you 1,000 times to encounter one failure, that doesn't mean that when the TAs run it on their machines, that it's not going to fail 100 times in a row. So, yeah. Follow the pseudocode we've posted. The other recommendation that I have for you is to use the semaphore implementation as a guide, especially for things like create and destroy. The other recommendation that I have for you with implementing your locks is it is absolutely critical that you initialize all the fields of the lock. So for example, when you create the lock, you need a held field and an owner field. Don't leave them blank. People too often coming from 136 assume that when you create a Boolean variable and you don't initialize it, that its default value is false. And that when you create an integer and you don't initialize it, that its default value is 0. And that is absolutely not the case whatsoever. You have no control or no idea what the initial values of those variables will actually be. And I have seen this time and time again show up on assignment 2 and assignment 3 where people have not initialized those variables in the lock. And it works for one assignment by some miracle, but then when you fix the memory problems in OS 161 and assignment 3, it stops working. And people are like, I don't understand what happened. They were working before. Yeah, they were worked before because your memory wasn't working properly. And now that it is, the bug that you made before is now actually coming into light. So please, please, please just initialize your variables. It's really important. Question on Twitch says, so to change the number of CPUs, we just uncomment a line and comment out another. Yes, you could do that, or you could just change the number after the word CPUs. Do not make it more than like 8 or 16 because it won't like you. We're not going to test with that many anyways. I think we use 4. We might use 8. We might use actually 1, 2, and 4 if memory serves me. So we use a few different configurations. But only for this assignment do we do that. We don't do that for the next assignment. Okay, so that's how you're going to test assignment or the locks implementation. Then you need to, once you are 100% convinced that your locks are working, then implement condition variables. Condition variables, we've talked about how to implement them in one of the episodes way back. We've actually presented you some pseudocode. They're very easy to implement, very few lines of code, and I know in the starter code that you have, it indicates that for signal and broadcast only, you should own the lock that is passed into that function. You can check if you want, but we're not requiring it. The only place you are required to actually own the lock that's passed into a CV is in CV wait. You absolutely must. And I know there's this temptation of not checking using lock do I hold in CV wait and letting the K assertion failure actually happen inside of lock release, but you will lose marks for that. And the reason you'll lose marks for letting lock release throw the assertion is because that's not actually where the error happened. The error should have been detected in CV wait, not lock release, because they represent two fundamentally different reasons for throwing an assertion failure. So make sure you're using lock do I hold and use that in CV wait. Please don't add any spin locks to your condition variable. You don't need them. Anything like that. Now, to test your condition variables, we have another test. That's SY3. And you should test it in the exact same way that you test locks. Now, there's going to be some temptations to run tests back-to-back in OS 161. I'm going to advise that you don't do this, and allow me to show you why. This is probably not going to work because my computer has updated, but let's give it a try. This is 161, kernel SST1. Okay. So here I have the tests menu, and I'm going to try to run the lock test back-to-back twice. So I'm going to run SY2. Yes, it's going to take some time. It could take 10 seconds. It could take 30 seconds. This is expected. Locks are going to slow things down a little bit for some of these tests. Now, if I try to run SY2 back-to-back again, it might work, or it might go into some kind of infinite loop and take a really, really long time, or it might actually crash. This is not you and your fault. This is actually the fault of OS 161. I'm actually going to kill it here because I don't want to wait forever and kill my computer here. You cannot run tests back-to-back in OS 161 until assignment 3. What that means is that you need to be doing these tests from the command line, one at a time. So to run the test from the command line, after you specify which kernel you wish to use, in the quotes, put the test, and then a semicolon Q, and it will start the OS, run your test, and quit. And that's very useful because you can add that to your testing script. Question on Twitch is, what's the difference between UW lock test and the normal lock test? They're both just lock tests, and you should run them both. Because we're running them both, right? So you should run them both. By the way, all of these tests, there's no secrets here. Like, if you want to know why we don't do public testing, number one, because it's kind of hard with an operating system. But number two, because we're giving you all of the source code to all of the tests that we're going to run. So since you're also third year students, we're assuming you can look at the test code and figure out what the right output should be. Coincidentally, also, if we will not be answering questions on Piazza of the nature, is this the correct output? We will not answer those questions and tell you whether it is or is not correct output, simply because you have the implementation. You have 100% of the source code to all of the tests, and you should actually be reading that. All right. So the question on Twitch, what does UW stand for? I don't know, University of Washington? University of, I don't know, what's another word that starts with W? Walls? It's our own private, it's a test we added, obviously. All right. University of Washington, by the way, is the other UW. All right. So the tests, just to remember, are you can access the test menu with the question mark T. And we run SY2, SY3, and UW1. Those are the three tests we do for locks and condition variables. Okay? All right. On to the next part. So when you are 100% convinced that your locks and condition variables are fully functional, only then do you move on to the rest of the assignment. And the reason is, if you try to move on to the rest of the assignment before you're convinced that assignment 1 actually works, or your locks and condition variables work, you're going to have a really bad time with the rest of the assignment. So let's talk about the rest then. So I'm going to start with the A2A guide, which is the first 4 process management calls, and then we'll do the A2B guide, which is the second one. You are responsible for all of this in a single assignment. So we are asking you, after you've implemented locks and condition variables, which should take you 5 minutes, we want you to implement the 5 process management calls that OS 161 supports, which is fork, wait PID, get PID, exit, and execv. So remember that fork is going to create a copy of the current process, and it's going to return a different value to the parent and the child. Wait PID lets us wait for a process who is our child to terminate, and then gets any exit code or status messages that they left behind. Get PID gives us the PID, that unique identification number for the current process. Exit terminates the process that is running and passes the code back to its parent, and perhaps wakes the parent up. And then execv doesn't create a new process, but does change what program the process is running. So what we're going to do now is we're actually going to walk through the implementation of each of these functions. Now, some students are like, why are you doing this? You're giving away all of the implementation details for this. Yes, in a lot of ways, we are giving away way too much assistance for this assignment. The reason why we do it is because we make observations in office hours, and we make observations on Piazza about what are the most commonly asked questions. And we could answer those questions individually 100, 200 times a term. But, it'd kind of just be easier to address them all at the beginning. And then we can actually spend time helping you with the more unique problems. So, yeah. If, however, you're like, this is too easy, then don't look at the guides. Don't look at them if it's too easy. We don't care if you look at the guides or not. That's up to you. All right. Anyways, that's a little rant. Let's look at fork. What needs to happen? So we know we need to create a new process. We know that new process needs to have the same address space or the identical contents of the address space as the parent. We need to set up a parent-child relationship, and so on and so forth. So let's go over the steps in detail. So we have to create that new process structure. Okay, it's pretty easy. We need to create a new address space, allocate the memory for it, and then copy the contents of the parents into the child's address space. And then we want to attach that address space that we just created to the child process. Not so bad. Once we know that's all going to work, we can assign a PID. Now this line here, we have this kind of in the middle. And I want to tell you, it doesn't have to be here. There are many other places where you can assign a PID to the child process other than this point right here. It's your choice how you implement this. This is a guide, not a rule book. So after you have assigned your PID, you're going to set up the parent-child relationship. Obviously, you don't want to set up a parent-child relationship unless you know the process is actually going to work out. And then we need to create a thread for the child process. Because remember, every process, if it wants to execute something, needs a thread. And when you actually create a thread structure, it doesn't actually create any threads for it. So we need to create a new thread for the child process. And then here's the weird thing. We need to take the parent's trap frame from its stack and we need to put it onto the stack of the child process. And the reason for that is we need to make sure that the parent and child process both return to the program at the exact same instruction with the same contents in the register, with the exception of the return value for fork, which will be different between the parent and the child. So we need some way of taking the trap frame from the parent and giving it to the child so that they'll be able to continue from the same instruction as well. Once we have that onto the stack, we call this function called MIPS user mode in the child process, only the child process. And that is going to fake a return from an exception so that we can actually go back into userland. And, it can continue executing and all those lovely, lovely things. All right. Seems like a lot of code, but doesn't seem that bad. And it's actually a lot easier than it sounds because a lot of this is already implemented for you. You just have to call the right functions. So for one, you're going to need to update the process structure and add your own fields. That's a given. It's missing a lot of fields. You can add whatever you need, but don't change anything that's there. So there's already a bunch of items in the process structure. They need to stay there unmodified, but you can add as many additional things as you need or want. To create your process structure, you don't need to, allocate the structure and all that stuff manually. You're just going to call this function called proc create run program. And you're done. That's it. You're all done. The process structure will get created. And there is one more detail. You need to check to make sure it actually happens successfully. So proc create run program can return an error code or it can return null. And if it does return an error code or if it returns null, it means it had a problem creating a new process, usually because you ran out of memory. And believe me, that happens a lot. You need to check to make sure that proc create run program actually returned and didn't throw an error. And if it threw an error, then your sys fork shouldn't cause the kernel of the operating system to crash and die. You should be forwarding that error back to the user program to let them know that you couldn't do the job. That being said, all of the tests that we are actually going to be running in OS 161 are successful tests. That is, none of them will be testing your errors. So why bother checking then? Because it's really good for you for when you're trying to debug this assignment. Because you know all the tests should succeed. So if they don't, doing these error checks is going to kind of be a way of validating or finding where the bug might actually be. After you've created the process structure and you know it's a valid structure and all those things, then I said you needed to create an address space. And we want it to be a copy of the parents. So you might think, okay, well, I've got to figure out the size of the parents. I've got to malloc it, and then I got to copy it over using, memcopy. Nope, no, you don't have to do that. All you have to do is call one function, ascopy. And ascopy is going to take the parent's address space and a pointer to a pointer of your address space. And it is going to, very tired today. It is going to actually allocate space for the address space and copy the parents into the child's. So all of the work for doing the address space is done in ascopy. The only thing it doesn't do is attach that address space to your new process structure. You have to do that yourself. Now, do not call kerproc setas to set the address space, because that will set the parent's address space, and we don't want to do that. But you can look at the code in kerproc setas to see how can you safely set the address space of a process. So use that as a guide for setting somebody else's address space, not your own. The other thing is to remind you of is that ASCopy can return an error because of, ran out of memory. Common bug in OS 161. All right. So the next thing is a question on Twitch. Could you provide the function signature when you introduce them or point us to where to find them? So proc create run program is in proc.c. And ASCopy is in, I think it's in dumvm.c, but I don't remember. If you Google, or if you grep, you'll find them, because they're not really used all over the place. Okay. So you've got your process structure. You've copied the address space. Now you need to do something like, set the PID. How do you set the PID? We don't care. Do whatever you want. Have fun. Okay, maybe not that much fun. The thing you need to know is no process can have PID 0, because that's the kernel. And because if a process actually had a PID named 0, then when fork returns 0, it would actually be returning somebody's PID and not indicating that it's the child. So that would be a problem. PIDs have to be unique. Every process has to have its own. And if you look at older versions of this assignment, they said the PIDs had to be reusable, because in real life, PIDs are reusable. Yours don't have to be reusable. It's impossible for us to test that. And we don't really want to look at your code. So if you want your PIDs to be a counter, a global counter, and you just increment the counter each time, you go right ahead and do that. It is totally fine to do that. Sorry, looking for my little color wheel thing here. Well, now I look red, but anyways. The fun things you can do with light, right? You can make everybody look super, super scary. Which that just screws up the green screen. Anyways. I shouldn't have this much fun with it. Lighting is a powerful thing in film, okay? You can do all kinds of fun things. All right, so if you want to set a counter and just have the counter increment every time you create a new process, you totally do that. It works just fine. The one thing I will say is the counter is a shared global variable, which means the counter is going to need some kind of mutual exclusion, because it's entirely plausible that multiple processes are forking at the same time. So, protect it. You can use a semaphore, you can use a lock, you can use a spin lock, I don't care. It's a counter. If you're doing the counter approach, you could use a spin lock, because it's just adding one, so it's pretty simple. If you do decide to use reusable PIDs, there's different ways that you could do that. You can keep a table of PIDs that are in use, and or just the usage of each PID, and then choose one that's not in use. You will not need more than 64 unique PIDs, because we don't test with more processes than that, because the system will crash and die. So be very it's a reasonable number of reusable PIDs. Another cool approach I've seen people do to using reusable PIDs, and it's not perfect, is to use this address of the process structure. Now, the problem with that is that's an unsigned int, and PIDs are signed ints. So you'll end up with negative PIDs, which is a problem, but you can just do a bit shift and it kind of works. Or you could just do a counter, which totally works. All right. So after you've done that, you, of course, also need to set up the parent-child relationship. That is also entirely up to you, but the easiest thing to generally do is to have each process keep a pointer to its parent and a list of pointers to its children. you could also keep the PID of your parent and a list of PIDs to your children. You don't need a list of parents because you can only have one parent. It's not like humans where you actually technically you need two parents to actually be alive. But so we just have one. So it's like a worm or something. I don't know. Okay. So one parent, list of children. Do it however you want. If you are trying to create a dynamic array, OS 161 actually has a dynamic array already built in, and I'll show you where you can find it. So if you go into that is so not the directory we're supposed to be in. Over here. So the dynamic array, so if you're in the current directory, go into the lib directory. And inside lib, you'll see array.c. And array.c is a dynamic array already implemented for you. And I really recommend that you use this instead of trying to create your own linked list or anything like that, because this is already implemented and it's already tested, which is really nice. Now, so that's where you can find the implementation, and you can find the header files in the include directory. And then if you want to know how to use it, if you go into test, there is array test.c, and that's actually going to show you how to use the array, the dynamic array. One of the things that I want to remind you of is if you try to remove, like let's say you have a for loop for I equals 1 to n, and then you do remove item from array. That's going to fail because the array is dynamic, and as you remove things, it actually physically shrinks. So n will go out of bounds. So you kind of have to check the length of the array each time. Something like that. So just pay attention. Don't go implementing your own linked list. It's not worth your time. And that's generally true in assignments. Don't implement something if it's provided to you. All right, that's A2B. We don't want that. We want A2A. There we go. Okay. So you create your PID, you create your parent-child relationship. The next thing you need to do is create a thread for the process. You can create a thread using the thread fork function, which creates the thread structure and assigns the thread a start address so it knows where to start executing instructions from. So when you create thread fork, you need to make sure that you are attaching this new thread not to yourself, but to your child. So you need to make sure that the second parameter of thread fork is a pointer to the child process. Okay, child process. And then what is going to be the entry point function? So you need to create a function, and there is one already in existence. It's empty, called enter forked process. You're welcome to use that, but you'll need to change the signature so that it matches what thread fork expects. So you need to convert it to void start and unsigned long. And if you don't make it exactly that, it will not compile. And this function here, or whatever you decide to call it, is going to be responsible for setting up the trap frame for the child process, but also making sure that the child process will return from the exception and go back to executing the user code. So why do we need to pass the trap frame to the parent, from the parent to the child? Well, we know that two processes after fork continue from the same point of execution, which means that the new process, which has never executed an instruction in its life, needs to have all of your register values, and it also needs to know what your program counter is. Now, it already knows what your stack is because it got it when you did the address space copy, but it doesn't know what the values in the registers are, so it doesn't know what instruction it's on right now. So inside of enter fork process, we're going to take the parent's trap frame, which contains all of that saved register information, and we're going to shove it onto the stack of the child process. That probably sounds like it's a really complicated idea. It's actually really, really easy. And the reason why it's really easy is because all you have to do is take that trap frame and put it on the stack. What kinds of variables go on the stack? Local variables. So you're just going to make a local variable trap frame and then dump the contents using a shallow copy of the parent's trap frame into it. Shallow copy is totally fine here. There's no reason at all to use memcopy on these trap frames. None at all. Now, here's the tricky bit. In our heads, We look at a sequential program and we forget the fact that context switches can happen at any time, and we have no control over the order of thread execution. So we look at our implementation of fork and say, oh yeah, we forked the thread will get the parent's trap frame, and then the parent will come back and run, and that's not how it works. What can actually happen is the parent thread, the parent process, may call thread fork, but that thread may go to the back of the queue, and then the parent may actually finish executing sysfork, and then their trap frame gets restored, and then when the child process runs, that thread doesn't, when it tries to copy the parent's trap frame to itself, well, the parent's trap frame disappeared, and so it copies garbage and things don't work. So we have a bit of a synchronization problem here, and there's two ways to fix it. Way number one is to use synchronization primitives to force the parent to wait for the child process to grab its trap frame before it's allowed to return from sysfork. Could do that. That's going to be slow. We don't want it to be slow. So here's the trick. It's not a tricky solution. Make a copy of the parent's trap frame in the kernel heap using kmalloc just before you call thread fork. Pass a pointer to the copy into enter fork process, and then in enter fork process, after you put it on the stack, free it. This is a unique copy. When the parent returns, it will not be able to destroy it because it belongs to the kernel. So that's a really easy way to do it without synchronization, is just make a copy and pass the copy in. Ta-da! Don't forget to delete it though when you're done. All right. Now, are you done? Not quite for fork. Here's one of the big problems. If we finish with fork with that, then we wouldn't actually have set up the return values for the child process's fork. Now, we don't have to set up the return values for the parent process's fork because they're kind of already handled for us. But the child process doesn't return through the system called dispatcher, so we do need to manually set its return values. So you need to set the return code for the child, which is V0. In the trap frame that's on its stack, you need to set it to 0 to indicate I'm the child. And then A3, you need to indicate no error, which is also 0. And then you need to increment the program counter to the next instruction so that the child process doesn't start throwing system calls. We don't want it to do that. And then you call MIPS user mode to actually return from that fake exception so that the user program can continue. Now we have some question marks in here because we're expecting that you will be able to fill that in yourself. Years ago, we wouldn't actually give you this pseudocode, but again, this is one of those things where we'd get 200 questions on Piazza and a lineup down the hall, about 40 people long, all asking the exact same thing. So when we find that kind of situation, we have a tendency to just add it to the guide. That way we can help you all in advance, right? All right, so that's fork. It's actually pretty easy to implement. Wait, PID, and exit are the hardest, and you need to implement them together because they rely on each other. Get PID, I'm not helping you with. It's one line of code inside a function. We're not going to go over that one. Wait, PID, and exit need to work together, so you should implement them together and only implement them after you've tested fork. Why do you need to implement wait, PID, and exit together? Because wait, PID is going to wait for a child to terminate, and it's only going to wait for children to terminate by a call to exit. Exit is going to set up the exit status and exit code, which is the information that wait, PID wants once the child has terminated. So implement these two together. So remember first that wait PID can only be called on your child process. And that means that inside of wait PID, you need to validate that the PID that's given to you is actually one of your children, which is why you need to know who your children are. If it is not one of your children or the process simply doesn't exist, you can throw an appropriate error code. We're not going to check what error code you are throwing. You throw the one that you think is most appropriate. Not an assertion failure. You're returning an error code. These functions should not... I just poured cranberry juice all over the floor. Whoops. Or at least all over my arm. Oh, one of those days. So what you want to do for this is, if it's not your child process and it's not a real process, you can choose which error code you throw. Again, we have no erroneous tests, so it's really up to you which code you throw. Don't throw a goofy one. Throw one that actually kind of makes sense. So if the PID is one of your children, then you should proceed with the implementation of Wait PID. And what you're going to need to do is check, is your child alive or dead? So you might want to have a status message inside of the process that indicates whether the process is alive or dead. However, because that would be a shared variable in the process structure, you need to protect it with a lock. And before you can check whether your child is alive or dead, you need to acquire that child's lock and then check if they are alive or dead. If the child is alive, then the parent process needs to go to sleep. We recommend using locks and condition variables. And I would also recommend that the parent goes to sleep on the child's condition variable, because it is waiting for the child to terminate. And then when the child terminates, that is, it calls exit, the child should signal, it doesn't need to broadcast because you only have one parent, it should signal the parent to wake back up, which will cause the parent to go back to executing Wait PID. At which point, if the child has terminated, inside of Wait PID, we need to get the exit status and exit code. This information, as long as you have a living parent, needs to be kept in the kernel of the operating system in some form while you have a living parent. And because the parent may call Wait PID on you and may ask for this information. So as long as a process has a living parent, then you must keep the exit status and exit code around. When Wait PID gets those two numbers, we're going to use a special macro called mkWaitExit, which takes only one parameter, but it's going to combine the exit status with wExited to create this master code, and that is what you're going to return to the user program as the reason why this process actually terminated. So that's kind of fun, right? I think it's fun. And you already have a stub implementation of Wait PID, which actually has most of that code in it already, so you just need to make a teeny tiny update to that little bit. I mean, you've got to do the other stuff, but yeah. Now, what happens if the parent exits before the children? So if the parents exit before the children need to stay alive. However, if any of the children are terminated, so that is, they're zombies, they still have some data lying around, but they're technically dead, then when the parent dies, any zombie children should be fully deleted. When the children die, the parent should not be deleted, because we don't do that. There's no concept of, inheriting or adopting new children in ROS. When a child exits, if its parent is not alive, that is, its parent is either a zombie or doesn't exist, then the child should fully delete itself. And the reason for this is you only keep the exit status and exit code, and you only create zombies when you have a parent that is alive. The second your parent is no longer among the living, then you can delete yourself. Okay? So keep that in mind. This is why you need to implement this with exit, is because the two functions work hand in hand. And this is where 80% of the difficulties with the assignment actually come from, is getting the synchronization correct between these two functions. The extra white noise is a vacuum. I'm guessing they found a spider in the basement. All right. So here's the macro that you're going to be using to combine the two status, the information together. And if you look at previous versions of these slides, you'll notice all these extra options and features you can implement for Wait PID. Don't do it. This is not a course with bonus marks. If you implement all these extra features, we're never going to know. So don't bother. Why do extra work if you don't have to? Like, presumably you have CS351. You could probably do that. if you finish early. All right, I'm not talking about get PID. We were talking about exit. I'm not going to add any more to this. We have 3 cases here that we've listed for when you can fully delete a process. That is, if its parent is already exited, if you are exiting and your children are dead, you can delete your dead children. And the other thing is if your parent has already called wait PID. So you can only call wait PID on a child once. Think of it this way. You're conducting an autopsy on this dead process. After you've conducted the autopsy once, why would you do it again? You already got the information. And that's what should happen is after somebody calls wait PID on the process and you've got the exit stat and exit code, then you can fully delete the process because we've retrieved the information that was left behind. So you can't call wait PID back to back on the same PID. It should fail the second time. All right. So that's the end of the A2A guide, which talks about the first few system calls. Now I want to switch over to the A2B guide, which talks about the final system call or process code. And that is execv, which is going to take the current process and it's going to change which program it runs. So first off, there's actually another function inside of OS 161 that does pretty much this thing from inside the kernel. So it's missing a few steps. And that's the function called run program. And when you start a user program from the little menu, this is the function that actually runs. And what it does is it opens the program, it creates the address space, it loads the address space. That's this load alpha function. It creates a stack and then it calls enter new process to actually, set up the entry point address and move the thread into the ready pool. Okay, well, this is pretty close to what execv needs to do, right? Execv needs to open the program. It needs to create the address space. It needs to load the address space and set up the stack. There's just a couple extra details. Like the program name isn't already in the kernel, it's in another user program's address space. And we also need to keep all the arguments for the program, which one program doesn't currently support, but you need to add for A2. So we also need to we need to grab the arguments for the program from either the kernel for run program or from the user address space for execv. We need to copy those into the kernel. Once they're in the kernel, then when we're setting up the stack, we need to copy them back to the new program stack so it can actually access them. So there's a few extra details between run program and execv. But what I recommend you do is when you start implementing execv, take the contents of run program and copy and paste them into sysexecv, because that will make your life easier. So this kind of in gray here are the lines that would be completely identical, that is unchanged. But there are, as I said before, a few little changes that you're going to need to make. First off, you need to get the name of the program and all the arguments for the program's execution from the old process's address space. So from the process's address space, you need to grab that. That's not that simple. There are some special functions we need to do in order to do this safely. And we'll go over those functions in a minute. So we're going to copy first the number of arguments. The arguments are stored in an array that is null terminated of pointers to strings. So you're going to have to copy, in order to figure out how many arguments, you need to copy each pointer in. And when you get a null pointer, you know it's the end of the argument array. And so you just count how many string pointers do you get before you get a null one. Then you need to copy each of those arguments into the kernel. So the actual strings, not the pointers, you need the actual strings into the kernel. And you're going to do a similar thing for the program name. Now, one of the biggest mistakes I see people make here is they forget the fact that you actually need to allocate memory in the kernel in which to store this information. So if you want to actually do if you want to copy the string arguments into the kernel, you need to allocate space for the string arguments in the kernel. When you are creating the stack, so you're going to do all that stuff you did before about VS Open, creating the new address space and load alpha, literally just copied from run program. This function isn't very long, by the way. And then you need to copy all of the arguments from the kernel into the new address space. That is into the new stack. This is the trickiest part of this function. We'll talk about it in a minute. So my recommendation for you is you need to make a new version of ASDefine stack that can set up all the arguments onto the stack for you, because run program is actually going to need this as well. And instead of having to write it once in run program and once in execv, write a new ASDefine stack and have them both call it. That way, if you implement it correctly once, the other function can take advantage of it. Good design, right? And then you need to change the arguments of enter a new process to let it know, hey, I have arguments and here's where you can find them. And don't forget, of course, to delete the old address space because we don't need it anymore. So that is execv in a nutshell. Let's take a little bit of a closer look at some of these. So first off, you'll note this big caution at the top. Maybe I should color this in red. This part trips up many students. So you have to count how many arguments there are. And there's this temptation to just, well, here's the address of it. Let's just look. Is it null or not? That's not safe. The problem is you shouldn't trust in the kernel. You should never trust a user address. It's a user program. This is a foreign piece of code. You shouldn't be touching that memory unless you are certain it's going to work out. So while it will technically work for this assignment, we don't recommend it. You should use these very special functions called copy in, copy out, and copy in star and copy out star in order to interact with addresses inside of the user's address space. And the reason is these special functions are going to validate the address first, so that the kernel doesn't throw crazy assertions and die. You don't want a blue screen of death because the user passed you a stupid address. That would be really bad. I mean, if you can imagine it this way, imagine you're on your Mac or whatever computer you have, and you've got this user program and it's got mistakes in it. What would happen if we didn't use functions like copy in and copy out is that you'd get the blue screen of death probably 10 times an hour. So we use these functions to validate the addresses in the user space before we actually, access the memory. So use them. So copy in and copy out, that's for copying stuff into the kernel and copying stuff into the address space and copying stuff out of the address space. Copy in and copy out are used for fixed size variables, so things like integers and arrays and pointers. There is special functions for copying the strings themselves. There's copy in star and copy out star, and they work for null terminated strings. Now, when you're allocating memory in the kernel for the actual strings, you can use strlen if you want, but don't forget that it doesn't include the null terminator, and you're going to need to add 1 to the length because that null terminator is absolutely critical for this, or you're going to have a really bad time. Okay. So use these functions here. My recommendation is you're going to use copy, so the copy in, copy out, to count the number of string pointers to figure out how many arguments there are. And then once you've figured out how many arguments, you will allocate space for those strings. You can, instead of figuring out the length of each string and allocating the exact amount of space, if you want to just allocate 64 or 128 bytes per string, that's totally fine. We have no crazy arguments because no one wants to type that many characters. This course is not about testing every edge case and every crazy insane thing. We're not doing that, do you? So yeah, you can assume that the total length from each character and the total path name is going to be less than 120 bytes each. And if you want to make that assumption, that's totally fine. All right, so after you've figured out how many arguments and you've copied them in, then you need to put them back onto the stack, the new stack. But you don't just do it down. So OS 161 has this expectation that certain things live on the stack in certain places when you start a program, like you enter a function. And they call this byte alignment. And this is not something unique to OS 161. Every operating system has their own little quirk, own little requirements for how this works. Here's OS161's. Characters can be located at any address. Integers and pointers, this is actually incorrect. This should be 8-byte, not 4-byte aligned. What does that mean, to be 8-byte aligned? It means that their addresses are divisible by 8. Pointers to strings have to be 4-byte aligned. That means their address has to be divisible by 4. And the stack pointer has to be 8-byte aligned, which means its address has to be divisible by 8. There are little functions and macros that you can use to help you get the correct alignment, like user stack and round up. So user stack is going to be the address of the start of the stack, so the base of the stack before you put anything on it. And then round up, if you want to round something up to a multiple of 8, this will give it a number and round it up to the next power multiple of 8. Now, what does all this mean? It's all so confusing. Let us show you what we mean. So let's say we have the following command. We're running ls, and then we have 2 arguments, -l and Mr. Goose. Mr. Goose is so important, right? So first thing we're going to do is, starting at the bottom of the stack, we are going to push the strings themselves onto the stack. The strings themselves do not have to live at any particular address. That doesn't matter. So you can see here, we've got Mr. Goose with the null terminator, and we've got -l with the null terminator. You'll also note that we've pushed the name of the program onto the stack as well. And that is because the first argument, and you should know this from playing around with C, argv0 is the name of the program. So we're going to push it onto the stack too. And then we will put the array of pointers, the null terminator array of pointers to the arguments. And it's important that each of these addresses live at an address divisible by 4. So you can see here, this is divisible by 4, 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 and this is divisible by 4. You may need to put some empty space between this array of pointers and the actual strings on the stack, and that's okay. When you are building the user stack in your special function to set up this user stack, you're going to be tempted to use things like kmalloc. Don't. All of the memory of the stack is yours. It's all yours. You do not need to kmalloc it because you already own it all. You are going to compute the address and write to it. And this is one of those rare programming times where you don't need to malloc before you write. Calculate the address and write to it. The memory is already yours. So it's a little weird to think of it that way, but when it comes to putting things on the stack, calculate the address and write to it. This is the number one place where people fail on execv, is getting these arguments onto the stack correctly, which is why I recommend you don't actually attempt this until you have the execv without arguments working first. In fact, we have these suggested steps for execv. So first suggested step, copy run program into execv. Second step, after that works, you are going to implement the copying of the program name into the kernel. And use kprintf to print it into the screen so that you know you got the correct program name inside the kernel. This is where you can debug with some printfs. It's okay here. And then make the modifications to execv to actually load the program. So do not do anything with the arguments until you have this working without arguments. And there are many tests. I think Hog Party has no argument passing. So make sure you get execv working without arguments before you attempt arguments. Once you have execv working without arguments, then count the number of arguments and print that number onto the screen. Make sure you're getting the right number every time. When you have the right number every time you test it, then add the code to copy the arguments from the address space into the kernel. Print those arguments from the kernel onto the screen, so using kprintf. Once you have validated that the arguments are all correct every test, Then and only then, in a final step, add the arguments to the stack. If you do all of this together and you have a problem, it's really hard to debug, which is why we're recommending this stepped approach, because if you do it in the stepped approach, you can at least know that everything beforehand was working, and so your bug is going to be down here. But if you do it all at once, I don't know where your bug's coming from because there's too many possible sources. Okay, so that's why we have this recommended stepped approach. One other thing I want to mention is make sure that you are not actually writing to this address here. Okay? Because that is actually not a part of the kernel, or not a part of the stack. That's a part of the kernel. Okay? Now, one last thing I want to show you. So I've showed you all 5 of the process management calls. There's something else I want to show you. Let me go over here. We're going to go to the course website. Hoping, of course, that the course websites are up and running. It is so not the address for this. Okay. So go to the course website and go to assignment information. If you look under Assignment 2, you'll see Assignment 2 Marking Report. There's also Assignment 2 Hints. You should read those before you do the assignment. But go into Assignment 2 Marking Report. This is your magical grades sheet. It tells you how many marks you get for each thing. So there's the lock implementation, condition variable implementation, and testing, and all of that stuff. And then for system calls, we actually list each of the tests we are going to run. Now, these are all user tests. They will be found in the user directory, not in the kern directory. You have all of the source code to these tests. We will not be telling you if your output is correct because you have the source code and you can just look at it. These are all the tests we're going to run. So one fork just uses fork and exit. Actually, I don't even think it has an exit. PID check. Wide fork is using all of them except execv, same with fork test. Hog party and sty use execv but no argument passing. And then the last 2, so there's arg test and arg test use argument passing from execv, and add uses argument passing from run program. So only these last 14 marks rely on argument passing. Now, the one thing I will say is all of hog party, sty, arg test, test. These all rely on fork and wait PID and all of that. So make sure that's working before you do this. Now, what happens if you implement this and you work so hard and you fail these tests? Are you done? No. Relax. We have these things called inspection marks. If you get less than 31 out of 62, so if you get less than 50% of the testing marks, we have these mercy marks. A TA will go into your code, and this is one of the only times they will, and they will look at your implementation. And they will try to judge how far, how close you are to actually having the solution. And you can get up to 31 marks. You do not get the summation of your test score and the inspection score. You will get the maximum of the 2. So if you fail the tests, you can still get a non-zero grade. So that's good, right? Always pay attention to these marking reports because they'll tell you all of the tests that we are running. Okay. So I'm going to leave it there for today. And in our next episode, we are going to start our biggest topic of the term, which is virtual memory. If you have more questions about assignment 2, of course, ask on Piazza, and I will try to remember to make a post about all of the common errors and mistakes and error messages you will see in OS 161, because you're going to see them a lot now. All right, so we will see you on Thursday then.